Just first two quick announcements. One is that we still have the conference picture that we're going to send to Alex Lubotzky. For those who haven't signed it yet, you can still do so. So it's in front here, so you can do it during the break, for instance. And also there are still some copies of the exercise sheets left on the table. So if you haven't picked them up and you still need some, you can still do it. Okay, so we're ready and excited to listen to the second part of Ori's lectures.
Thank you very much. Thank you for returning after yesterday. So yesterday we saw the punchline was we established a cutoff phenomenon for non-backtracking random walk on Ramanujan graphs. And the main ingredients were two. It was first that the spectrum of the operator which described the non-backtracking walk was let's say, was actually the trivial eigenvalue k, let's say the degree. I remind you that our graph is k plus 1 regular, so the degree of the non-backtracking walk is k. So the non-backtracking operator has the trivial eigenvalue k corresponding to the constant function, and the rest was actually contained in either the unit circle or plus minus 1. The second ingredient was that B is unitarily equivalent to 2 by 2 block diagonal matrix. I could write that. Yeah, okay. B was unitarily equivalent to a 2 by 2 block diagonal matrix. And in fact, once we have this idea, we can generalize it. So let's do a definition. Introduce a definition. A directed graph, so a K regular directed graph, which we call digraph, is a Ramanujan digraph if every eigenvalue lambda of the adjacency operator, so let's call this a K-regular digraph D, so of the adjacency operator of D satisfies that its absolute value is either K or bounded by the square root of K. So how does this relate to what we saw here? In particular, for a K.
I'm sorry, what's part 2? B
Here?
is...
Yeah,
What's,
I agree.
what's B?
B is unitarily similar to a 2 by 2 block diagonal matrix. So this, I should remind you, this is a weakening of being normal. A normal matrix is a matrix which commutes with its conjugate transpose. But that's not interesting. The interesting is that a matrix is not, that's a criterion. A matrix is normal if and only if it's unitarily equivalent, unitarily similar to a diagonal matrix. So here we're saying, oh, B is almost normal. It's unitarily similar to a block diagonal matrix with small blocks, but if you go back far away, it seems diagonal, right? In a quasi-geometric, in the coarse geometry. And we use that to replace normality. We really did, with an explicit computation. So for...
The definition is from K plus 1 regular?
No, K regular. Let me explain how this connects. If I have a K plus 1 regular graph, G, let's define a corresponding digraph, directed graph. So it will be the directed graph describing non-backtracking random walk on G. The vertices will be directed edges. In your original graph, and the edges, the edges are now directed because this is a directed graph, are the following. Here is one vertex. So this is a vertex because the vertices are the directed edges, and you connect this, so this will be a D edge, and this is a D vertex. You connect it to each vertex of the form VW, where W is not U. So this is a digraph whose vertices are the directed edges of the original graph, and the adjacency matrix of this new digraph, so the adjacency matrix of this new digraph is exactly the B matrix of the original graph. So that's how we encode the non-backtracking walk on the original graph in a simple walk, the adjacency operator on a directed graph. And now what Ihara, Bas, and so on tells us is that G is a Ramanujan graph if and only if the directed non-backtracking random walk graph of G is a Ramanujan diagram. So this is just a fancy way of saying what we said yesterday. We just give it a name. The point is that it turns out that this is really a high-dimensional phenomenon. So it turns out that Ramanujan digraphs occur in higher dimensions.
Sorry. In that construction, you start with a digraph or you start with a...
No, I start with a, okay, let's do an example. So this, let's say this is my G. So the new graph will have two vertices, four vertices, one for this edge, one for this edge, and another one for this edge, and another one for this. So I have four directions, four edges on the original graph, and non-backtracking will connect this to this, because this is a non-backtracking path, and this is a non-backtracking path. So my new digraph has four vertices and two edges. And they exactly encode what is the dynamic process Markov chain that non-backtracking walker does here. So it's just a machinery to describe non-symmetric random walk, but it turns out to be really, really useful to think about walks in high dimensions. And I should say that this for me is already high dimension, because usually when we talk about graph, we walk on vertices, we study operators on the vertices, and here we went one dimension higher, went to the edges, we studied things that happen on the edges, we encountered non-normal operators which don't exist on vertices of buildings in general, and I kind of gave you a hint how things correspond to the Iwahowiec algebra of the algebraic group. So in a sense, I want to say that if you want to do things with high-dimensional expanders or high-dimensional combinatorics of buildings, start with edges of a graph. There are interesting things there that we still don't see. These are pretty recent results. And people have studied walks on graph for a long time, so there is more to say. Okay, so what do I mean that they occur in higher dimension? Oh wait, before that, let me say, just connected to what we did yesterday. So here is really an exercise now, or let's start with the definition. A matrix is R normal if it is unitarily equivalent, similar to an R by R, or let's say to block diagonal matrix with blocks of size at most R by R. They can be small if you need them to be. So this is an R normal matrix, and we say that digraph is R normal if its adjacency matrix is, and then we would say that a family of digraphs is almost normal if all members are normal for some global R. So, for example, if we take a family of Ramanujan graphs and we look at the digraphs of non-backtracking walks on these graphs, we get a family of almost normal graphs. In fact, they're all too normal. And here's the exercise, generalize what we did yesterday to prove that if an almost normal family of Ramanujan digraphs has cutoff. And in fact, you can even say that the epsilon mixing time will be bounded by log k, so let's say almost of k regular. The mixing time will be bounded by log k to the number of vertices plus O log. So you need to think how to generalize what we did with 2 by 2 block to R by R blocks. That's the exercise, but it's fun. It's linear algebra. We all like linear algebra because that's the only thing we can really depend on. And another thing I'll tell you is, well, where does the name Ramanujan digraphs come from, right? Ramanujan graphs should be the optimal expanders. And we have several ways of making that precise. So we can do it also in this, for the Ramanujan digraph. So here is a kind of an Alongo-Pana theorem in an almost normal family, or say infinite family of k regular digraphs the lim-inf of the, as you go over the family, the lim-inf, no, now I won't say the second eigenvalue because the eigenvalue are complex, but let's say the maximal eigenvalue, which is not k, will be at least square root of k. Okay, so this is lambda in the spectrum, but not the trivial one. Then the non-trivial eigenvalues go at least to square root of k.
For UK regular means that the out degree is k and the in degree is...
Yeah, both out and in, because I really study groups, and in groups you always have symmetry. This is also not hard. You can do this, find your favorite proof for a Lonbo panel and see how you change it to these settings, and maybe it will work. So, okay, what I want to tell you now is about a project with Lubotzky, and myself, where we set out to find what is the analog of all these stories for Ramanujan graph for Ramanujan complexes. And our goal was to find cutoff on Ramanujan complexes, and try this. And we found out that there is a very broad family of random walks on Ramanujan complexes which have the behavior of non-backtracking walk on Ramanujan graphs. And
what are you walking on?
exactly, that's the main question. And it turns out you can actually walk on anything except vertices. On vertices you can't do that. On vertices, okay, so I'll give you first our main example. So we define something we thought of as the unit tangent bundle of the building. I'll explain why we're thinking about it this way. So when you have a Riemannian manifold or even Euclidean space, and you're thinking about random motion, you think about Brownian motion. You think about a particle that goes everywhere it wants, and the analog in graph is a walker that walks everywhere he wants. But when you try to make it not turning back in the graph, you get to non-backtracking random walk. But in a manifold, let's say you have to pick a direction. And then what you're doing, you're not walking on the manifold, you're walking on the tangent bundle of the manifold. If you want a constant speed, you'll be walking on the unit tangent bundle. And you have a geodesic flow on the unit tangent bundle. So we're saying, oh, our idea was to construct a p-adic analog of geodesic flow on the tangent bundle. And it looks like this. So did we talk about colors of vertices in the building? So maybe we need first color. So let's recall that the vertices, I'm talking now on the building of EGLDQP. So recall that the vertices correspond to homothetic classes of the ZP lattices in QP to the D. And I like to think about it really as constant of D mod K, where K is PGL D ZP. So was that set? I think. Yeah, actually, yeah, it's the simplest part, like the lowest part of the BN construction. But you can see directly because this is the stabilizer of the standard lattice, ZP to the D, and the big group act transitively on all lattices. So this is the orbit stabilizer theorem. So now we define a coloring function on the vertices. And the coloring goes to Z mod DZ. And the color of the vertex GK is the p-valuation of the determinant of G. And we're in PGL all the time. So the determinant, so G is only one defined up to a scalar. The determinant will be changed by this scalar to the D. And then the valuation is well defined up to some multiple of D. This is why we're only in Z mod DZ and not in Z. Okay, so this is the coloring of the building. Yeah, we actually talked about coloring because we argued whether the action preserves colors or not for a long time. Okay. So here's the unit tangent bundle. And we really called it the unit tangent J bundle of the building. And
Wait, sorry, why did we argue? I mean, what was the argument on the preserving colors?
No, I didn't remember if we defined colors, and then I said we had to because we argued about color preservation for a long time. So
We
we
didn't
probably
use,
defined colors.
use like labels using the Coxeter diagram. But I guess that's
Labels on the edges?
yeah.
No, it's something different. Maybe that's why we argued because we were talking about color, color types and vertex colors.
Doesn't correspond to this.
But this is the coloring I will be referring to, not the. You're thinking about the labeling by the by the generators of the Veil group.
That's right.
No. That's something else.
And so what, the action is transitive on the color?
On the action of PSL is transitive on each color. The action of PGL is transitive on all vertices.
Okay.
Because you can really
PGL
change color
mixes the colors.
by matrices like this.
Okay.
Yeah, that's why we argued, because we want to be able to get to all colors. So it's a pair of a vertex and a cell. The vertex of a vertex, a cell of dimension J, the cell contains a vertex, and we have some restriction on colors, so it should have so let's call it V1, V2, so 0 to Vj, where V0 is V. So you can write the vertices such that the color of the Vj vertex is the color of the first vertex plus 1, plus j. So we want the colors to be increasing. So let me give you an example. Here we're in a PGL3 case, and the colors are 1, 2, 3. So it's, for example, the choice of a vertex and a cell where the colors are increasing by 1. So here it's trivial, but if you go to PGL4, and think about, so this is PGL3, but if you go to PGL4 and think about the j equal 2, no, j, let's say with j equal 1, then I'm allowing you to take the 0, 1 cell, but there are 2 and 3, and I'm not thinking about the 0, 2. So this one, it's not there. So you can actually also work on this, but the simplest case is this.
Do I take 3, 0 as well?
Hmm?
Do I take 3, 0 as well? Is it
Yeah, because we're in Z mod. The coloring really lives here. So this is.
Sorry, I don't understand your tetrahedron. I don't understand your pictures.
Oh.
So PGL, the first one is PGL3 is just a simplex in your building.
Yeah, that's a cell in the building. But
Okay.
I'm working on cells of different
So
dimensions.
you're working a 2 cell now.
So this is for j equal 1, but I could also take j equal 2, and then it would be a triangle.
Okay.
And here I can work on edges, triangles, tetraheders. I should say that j is at least 1, not vertices. So we're going, okay, what the idea is that we wanted to work on vertices, but with a direction. And this cell is supposed to show us the direction we want to walk to, and it's supposed to give us an analog of the non-backtracking walk. So think about this cell as that a direction living in the tangent bundle. And here is the flow.
The condition on the colors of Vj, you only impose it on Vj, or you also impose it on Vi or I small?
Sorry,
So,
you use J?
so it's
color Vj. Okay, no. So yeah, for heavy I, you're right. Yeah, the color here should be consecutive. Thank you. To tell you the truth, forget about colors. If you want to understand the you have to take colors eventually for the theorem to be correct, but stay for a while, forget about colors, think about a vertex and a direction, which is dictated by a cell. Don't look at the colors for now, they're there just to make the theorem correct, as Francois explained to me. They're not interesting. So here's the J-dimensional geodesic flow.
Excuse me, I have another question, because so you're saying in the PGL4 case that 0, 2 is not included, but why is 1, 3 included?
Here I have 0, 1, 1, 1 to 2, 2 to 3, and 3 to 0.
Yeah.
But I'm not allowing 1 to 3 and not allowing 0
Okay,
to 2.
yeah, but in your picture you're only putting across through 0, 2, that's why.
Yeah, but I only gave one example, one non-example.
Okay, so, yeah, okay.
Yeah. So the walk, you go from a vertex with a direction to, let's say this guy, if it's V0 to Vk, to all. So now I go to the next vertex, and all cells which looks like V1, V2, Vj, and I need to add something new, such that, well, first there's the color. So now the color of W should be the color of Vj plus 1. So I want to keep the consecutive coloring, but as I said, that's boring. And this is the interesting part. We only ask for V0, V1, up to Vj and W not to be a set.
So for instance, in the PGL4 example, if we're going on we're working on triangles, and we have to leave the chain. Start. Yeah.
Let's do examples. Yeah, that's a very good place to do some examples. Example. So let's say B is a tree. The building is a tree, and in the tree you only have j equal 1, and so you have a point, and you have an edge, and in this case the edge has to be of the right coloring because all edges in the building go between different colors. And you're allowed to go to W, and then W, and you maybe call it U. You're allowed to U, and you add here all the W's such that V and U and W is not in the tree. Now, the tree doesn't have triangles, but you could have repeating vertices here, and then it would be an edge in the tree. So actually the only thing that can happen is that W can be V. So I actually ruled out backtracking. So this is the non-backtracking. This is just the non-backtracking. But if we move to the building of PGL3, then I'm walking from a vertex, and let's write it as a, let's take j equal 1. So I only have an edge. So now I have an edge VU. And I'm going to walk to edges of the two pairs of the vertex, an edge containing this but only such that VUW is not in the building. So the picture would be, here is V and U, and I think about the direction given this by the fact that I know that this has color 1 more than this, and I'm going to edges like these. So I'm allowed to go to all the W's, but not this one, but not to this edge. So here again, this would be not allowed because VUW is a triangle in the building. And I want to show you what happened on the apartment.
So just a question, when you're changing simplex,
When
you can
what?
go anywhere in the new simplex?
Yes, yeah. That's the difference between Riemannian geodesic flow and p-adic geodesic flow. We really don't have like a transfer.
It's very local. It's telling you what to do within a simplex, but once you decide to get out of the simplex, you go wherever you want.
Yes. I want to, let's see, I want to show you what happened on the apartment. Because on the apartment, I actually know where I have to go. So if this is a vertex of color 0 and this is a vertex of color 1, and I'm sitting on this edge. So this is V and this is sigma. Where can I go? I cannot go here because this is, by the way, we call this the geodesicity. Because going from here to here is not geodesic, there is a shorter path. That's why we like the name. So I cannot go here because it's not geodesic. And I cannot go here because it's not geodesic. So you would think I could go here or here or here. But actually no, because this has color 0 and this is color 0. So this is not the coloring I want. This has color 2 and these have color 2. So these are disqualified by geodesicity and I can only go here. And then you continue and you get a flow on the apartment. So Indira, for your question, on the apartment you actually have a geodesic flow But the building is this branching of the apartment, and you get a branching operator.
So the restriction is really in the flats.
Yeah, and it's flat. There is a restriction, and the building gives us a random process.
But if you were to go up where the 0 is, that would be a geodesic in the one skeleton of the...
In the geometric sense, yes,
Yeah.
but then I could not write the following. The J geodesic, or let's write it like that way, the digraph describing geodesic, J geodesic flow on the building, on a Ramanujan quotient, Ramanujan complex. So, if the quotient of the building by some compact lattice is a Ramanujan diagram. And furthermore, it's also the factorial normal. This is easy. This is, easy because we know the classification of Ivahori spherical representation. So this is the theory of Ivahori. So in this case, the fact that we decompose to blocks comes from representation theory, because this is what representation theory was invented for. Decomposing matrices to small blocks when you have symmetry in your life. And that's exactly what it does for us. It decomposes to the irreducibles, and for each irreducible you only have finitely many Ivahori spherical vectors. Actually, the factorial, if you go to other undivided groups, then this will be just replaced by the size of the vector.
So there is an analog of this theorem for other types of...
Yes, yeah, we did something more general.
So then you have to define differently.
Sorry?
You have to modify the definition of the...
Yes, so eventually we have a very general criterion. So we were surprised to get such a general criterion. In retrospect it makes sense, but we only set out to do something very concrete, and eventually we understand what happened is quite general. So let's say a digraph is collision free if every pair of vertices have at most one path from V to W. So you don't have one path and let's say another path. It could be longer. You also don't have loops, because if you have a loop, you can take this loop twice, and that's a different path. Cycle. And here is the more general theorem. If the digraph describing some walk on the cells, on some cells of a building of any algebraic group G is collision free the digraph which describes this walk on Ramanujan quotients is a Ramanujan diagram. So you can do it with other groups once you find some walk which on the building doesn't have collisions. So think for a moment on non-backtracking walk on the edges of a tree. The vertices are now the directed edges. If from a directed edge you have a path to another directed edge, that's fine, but there are no two paths in the tree. And now you can show that the same happened here. In the building of PGL3, if you take this geodesic flow on edges, you could have at most one path from one edge to another. That is really like people, you'll hear people saying a lot that buildings are tree-like or generalization of trees. And in this is a really concrete way in which you see that. You have these walks which keep branching. You can get twice the same place. And this is this can give you Ramanujan digraphs from all dimension of all algebraic groups. I said yesterday that we don't understand what happened with cutoff. So today the situation is that we know how to prove cutoff for Ramanujan graphs, and for these walks on collision-free walks on Ramanujan complexes, and then more or less that's it. So it's kind of we use Ramanujan to do something that we expect to hold for expanders in general, but we really need Ramanujan to be able to prove that. The last thing I think I'll do now is to talk a minute about the simple random walk. But please ask me questions before.
How specifically do you use the structure of the fact that this is a building arising from an algebraic group?
Sorry?
How specific is it for the fact that this building arises from an algebraic group? I mean, if you would take...
That's what goes...
Case, you could basically...
What goes into the proof?
Yeah, kind of. I mean, especially does the algebraic data go into proof, or is it really like just properties of the building?
Okay, so there is the work you need to do to establish that some walk on the building is collision-free, and that's very algebraic, root system, veil length, and so on. You just make sure that you keep branching. And then there's the machinery, the Ramanujan machinery, which tells you that Ramanujan quotients are going to inherit this optimal expansion. And this is quite robust. At first, we really did it by analyzing the representation theory, taking the representation, finding the eigenvalues. We only did it for PGL-N, because starting to classify the representation of all algebraic groups over the p-adic is quite far. But eventually, we realized how we can replace everything by a soft argument, which has just to do with growth and decay of matrix coefficient and Harris-Chandra C function and tempered spectrum and so on. It's really like I was really amazed because that's the only project I actually worked on with my former advisor, with Alex Lubotzky, and I kept saying, yeah, okay, that is much more than we hoped to prove. Let's stop here. And he kept saying, no, we can do more. We can prove in data generality, I'm sure. And yeah.
So just to be sure, a digraph is a directed graph.
Yeah.
That's,
sorry, if I no, I said
but nothing. I mean.
Yeah, just to save same directed graph. Digraph.
Yeah, but. If you have one direction, do you have the other necessarily?
No.
So it could be any...
Actually, once I have one direction and the direction back, then I have loops, and so I'm not collision free.
Okay.
Oh, now I can point out why you don't have collision free walks. You don't have collision free walks on vertices of any algebraic group because of the commutativity of the Hecke algebra. You can show that this will force collision because you can take two paths, change the order you're walking in, and arrive at collision. So the fact that Hecke algebra of the Hecke algebra of the vertices is commutative is actually a nuisance when you want expansion, because backtracking kind of ruins expansion. We prefer to be non-commutative so you can branch out indefinitely. So what happened with simple random walk? So here Lubotzky and Perez did prove cutoff for simple random walk on k plus 1 Ramanujan graphs. And well, we saw that to do the spectral argument for the cutoff, you need to have square root of the degree, and Ramanujan graph only have twice the square root of the degree minus 1. What they do is that actually is an argument that people know how to do in graph theory for a long time. They say, well, I have this walk on the graph. I'm going to lift this walk to the universal cover, which is a tree. So this is my starting point here, this is my starting point here. And I'm going to look at the distance. So as I walk here on the graph, I'm going to walk on the tree. Sometimes I go back. And I'm going to look at the distance I am from the origin during the walk. And this distance is really a drifted walk. So it distributes like a random walk on n, which is 1 over k plus 1 to go left, and k over k plus 1 to go right, except at the origin. At the origin you always go farther away, but you rarely get back to the origin, so you can forget about it. You really have a drifted walk on the natural numbers. We know exactly how this walk behaves. Right? That's a Bernoulli process, binomial process. We have all kinds of estimates. We know that in the long run, you have central limit theorem. It tells you eventually that at time t, the distance is roughly, now you need to do the expectation, it's k minus 1 over k plus 1 t. And central limit theorem tells you what is the probability to deviate from the expectation. And the idea is that because of the central limit theorem, we can pretend that there are no deviation. So it's like, let's say you do this walk, and if you lift this walk to the tree, at time t you're really going to be here. Let's say that the central limit theorem would tell you that you really have to be here. There's no deviation. Then they tell you, oh, but if I know that I walked randomly on the tree and got to this distance, this is exactly like doing non-backtracking walk of this number of steps. It's just equivalent, because this is exactly how this sphere on the tree projects to the building. These are exactly the endpoints of non-backtracking walk of that length. And that they know how to do because we understand the spectrum here well. So what they get eventually is they get a cutoff, but the time is dilated. So the time is k plus 1 over k minus 1 log k n. Because it's non-backtracking random walk, which is k regular, and it's delayed a little because of coming back, and you have to compensate for this delay. This is the argument, which is very simple and people completely understood way back that simple random walk is like a non-backtracking random walk with stuttering. Like sometimes you delay yourself. And I think my time is up.
Yes, exactly.
Can I take 2 minutes just to finish this so I don't need to come back to this? So I just want to say that this was our goal in the walk on buildings as well, to say something on the simple random walk as well. So today we know how to do that for PGLN, because we need a better understanding of the building, or let's say PGLD. Let's work with Michael Chapman, who is a recent graduate in our department. And the idea is that you walk on a Ramanujan complex. So this is a Ramanujan complex. You lift your walk to a walk on the building. And then you do the retractions that Petra told us about. So this is the retraction to the apartment. So yeah, I drew the apartment, I should say, foot branching. So this is a building with many, many apartments going in all directions. But then you use the retraction to project you to a walk on the plane. And you get a drifted walk on the Euclidean plane. This was clear to us from the beginning that this should be the way to generalize the argument, to lift it to the tree, to the building, and project it to the apartment, but still it took us. We actually tried to do that with Alex and Eyal, with Lubotzky and Lubotzky. We didn't understand how to take things back, and now we understand how to do it. I think this is pretty because we really use here the structure of the building. You need to have a much better understanding than for this theorem. This theorem follows from decay of matrix coefficient. Here you need to decompose the simple random walk into geodesic flows in different dimensions. Actually, what we do eventually is we do like a two-dimensional central limit theorem. We point out where we're supposed to go, and then we build a sequence of geodesic flows which will get you to that same place. And we know how to analyze these geodesic flows by this theorem. I just wanted to promote this because I think there's more to do there. So this is like, I'm sure this can be done for more algebraic groups if you pin down the structure and how things look. Thank you.
Thank you, Ori, for this wonderful lecture.
Thank you.
Do we have questions?
Yeah, I have a question. You drew the graph, the geodesic flow for j is equal to 1 and PGL3, and for j is equal to 2.
Oh, great. I'm happy to. So that would be V. Let's call them V0, V1, V2. And you know that these are the colors. So you have to go, so this is V0, V0, V1, V2, and these are also the colors. And you need to go to V1, you always pick the next one.
You keep walking on the vertices.
Sorry?
You keep walking on the vertices.
No, I'm actually thinking about it as walking on triangles, but with a pointed triangle. Yeah. A triangle is a choice of a vertex.
Okay.
I go to V1.
The choice of a vertex is the vertex where you enter the triangle?
Well, I always keep all of the cell except the pointed vertex. I always throw out the pointed vertex and add a new one of the next color.
Okay.
So here it would be, I throw this guy out, I keep these two, and I add a new one. And so I'm going for...
So you're walking on galleries?
Yeah. Yes, I'll be walking like
this.
this.
Flow is going to give you galleries.
Yeah, it's going to walk like this.
So your geodesic flow is quasi-symmetric to a line.
Also here, as I said, on the apartment it becomes a deterministic process, and it will look like this.
Okay. But then you can change
But in the building, I'm branching.
Then you could change apartment.
Exactly. Yeah. So here, this requirement of geodesicity, actually there's no geodesicity here, except that I'm not allowed here to put V0 again, because then V0, V1, V2, and V0 will be a cell, and that prevents me from rotating by triangle, which would be very bad.
Other questions? If not, then let's thank away again.